A superheterodyne receiver, often shortened to superhet, is a type of radio receiver that uses frequency mixing to convert a received signal to a fixed intermediate frequency, shortly called as IF, which can be more conveniently processed than the original carrier frequency. It was invented by U.S. engineer Edwin Armstrong in 1918 during World War I. Virtually all modern radio receivers use the superheterodyne principle. A 5-tube superheterodyne receiver, made in Japan around 1955. Superheterodyne transistor radio circuit from around 1975. Block diagram of a typical superheterodyne receiver. Red parts are those that handle the incoming radio frequency signal. Green are parts that operate at the intermediate frequency, while blue parts operate at the modulation frequency. The dotted line indicates that the local oscillator and RF filter must be tuned in tandem.
The diagram at top shows the block diagram of a typical single conversion superheterodyne receiver. The diagram has blocks that are common to superheterodyne receivers. The antenna collects the radio signal. The tuned RF stage, with optional RF amplifier, provides some initial selectivity. It is necessary to suppress the image frequency, see below, and may also serve to prevent strong out-of-pass band signals from saturating the initial amplifier. A local oscillator provides the mixing frequency. It is usually a variable frequency oscillator, which is used to tune the receiver to different stations.
The frequency mixer does the actual heterodyning that gives the superheterodyne its name. It changes the incoming radio frequency signal to a higher or lower fixed intermediate frequency. The IF band pass filter and amplifier supply most of the gain and the narrowband filtering for the radio. The demodulator extracts the audio or other modulation from the IF radio frequency. The extracted signal is then amplified by the audio amplifier. Circuit description. To receive a radio signal, a suitable antenna is required. The output of the antenna may be very small, often only a few microvolts. The signal from the antenna is tuned and may be amplified in a so-called radio frequency RF amplifier, although this stage is often omitted. One or more tuned circuits at this stage block frequencies that are far removed from the intended reception frequency.
In order to tune the receiver to a particular station, the frequency of the local oscillator is controlled by the tuning knob. Tuning of the local oscillator and the RF stage may use a variable capacitor or varicap diode. The tuning of one or more tuned circuits in the RF stage must track the tuning of the local oscillator. How a superheterodyne radio works. The horizontal axes are frequency F. The blue graphs show the voltages of the radio signals at various points in the circuit. The red graphs show the transfer functions of the filters in the circuit. The incoming radio signal from the thickness of the red bands shows the fraction of signal from the previous graph that passes through the filter at each frequency. The antenna top graph consists of the desired radio signal S1 plus others at different frequencies. The RF filter second graph removes any signal such as S2 at the image frequency local oscillator intermediate frequency, which would otherwise pass through the IF filter and interfere. The remaining composite signal is applied to the mixer, along with the local oscillator signal, third graph. In the mixer, the signal S1 combines with the LO frequency to create a heterodyne at the difference between these frequencies, the intermediate frequency, at the mixer output, fourth graph.
This passes through the IF band pass filter, fifth graph, is amplified and demodulated. Here demodulation is not shown. The unwanted signals create heterodynes at other frequencies, fourth graph, which are filtered out by the IF filter. One of the prototyped superheterodyne receivers, built at Armstrong Signal Corps Laboratory, in Paris during World War I. It is constructed in two sections, the mixer and local oscillator, left, and 3 IF amplification stages, and a detector stage, right. The intermediate frequency was 75 kHz. One of the first amateur superheterodyne receivers, built in 1920 even before Armstrong published his paper. Due to the low gain of early triodes, it required 9 tubes, with 5 IF amplification stages, and used an IF of around 50 kHz. All-American 5 vacuum tube superheterodyne AM broadcast receiver, from 1940s, was cheap to manufacture, because it only required 5 tubes.